Okay, hi to everyone and good morning. My name is Sebastian Garcia, and well, this is a first talk of a series of how to model electromagnetics with the finite element method in Mathematica. And first of all, this is going to be focused on electrostatics. So what we are going to address today? Well, first of all, I want to show you that now we have a complete workflow for modeling electrostatic models. Then what I want to show you is how to model multimaterials in the electromagnetics fields. And then I want to show you how you can use these new functionalities to make multiphysics models. And in this case, we are going to see how to model a multiphysics actuator. In this case, we are going to couple an electrostatic model with a solid mechanics model. And for example, in this image, you can already see that you can compute many things. In this case, this is a 2D cross-sectional area of a capacitor where you can add different materials, for example, a dielectric and a vacuum that it is surrounding it. So these are the main things that we are going to address today. So basically, what we are doing in this subfield of electromagnetism, that is electrostatics, we are going to simulate the electrostatic phenomenon, that it is electric fields that are produced by stationary charges. And these stationary charges can be introduced by a potential difference or surface charge densities, etc. And these new functionalities are presented with these new functions. These are the PD components and boundary conditions that we have introduced for this subfield of electromagnetism. This is the first one that generates the equation that we need for the electrostatic equation. And then we have the boundary conditions. Essentially, it is the electric potential condition, that it is a Dirichlet condition. And then we have our Neumann values that we can use in our models. So first of all, we have the electrostatic PD component. This new function will generate automatically your electrostatic equation. And the capabilities of this function is that you can add your constitutive relation. For example, you can add a polarization vector or a relative permittivity of both at the same time if you want to describe a material that it is better described with a polarization or with a relative permittivity. We can deal with nonlinearities, such as a remanent polarization. And then we have other kind of parameters like adding sources, and that goes with volume charge densities, or we can add extra parameters like thickness or cross-sectional area when we want to apply symmetries in our model and scale the equation. So basically, this is a way one can generate the equation given the parameters that you want. So the most important thing is that we already have an electrostatic monograph where the whole workflow is described. First of all, we have an overview example where we show a 3D capacitor. In this 3D capacitor, we show how to compute the electric fields generated, and then how to compute the electric fields, the electric flux density, and then different methods to compute capacitance value with different methods. Then we have our electrostatic equation section where we give the whole theory behind how to model electrostatic, and then we give many different examples that showcase the different variations of the electrostatic equation. These include anisotropic relative permittivities or multiple materials and nonlinearities. Then we have a source section where we can add point charges, we can add line charges densities inside our domain for whatever reason you want. And then we have a section that it is named secondary quantities. In these secondary quantities, our focus was to show you how to make post-processing after doing an electrostatic model. In this case, we wanted to show you how to compute, for example, capacitance with the different methods that they are available. Then, for example, how to compute effectively the fields, the electric fields, and also how to compute forces. This is really useful because you can compute electrostatic forces between electrodes and between dielectrics, see how much is the force between these two objects. And we introduce how to compute these forces with a really general method that it is the Maxwell stress tensor. So it is really helpful to compute this kind of quantities. And then we have the boundary conditions, where we show you how to apply properly the boundary conditions for electrostatic models. And this has different conditions, and also how to use periodic boundary conditions for electrostatic models. So all this information is in this monograph that you can access to the new documentation of 14.0 version of Mathematica. So first of all, I want to show you how we are dealing with multiple materials in the electromagnetics context, and in this case, in the electrostatics, because there is a really big difference between modeling, for example, in heat transfer than in electrostatic. And the main reason is that in electromagnetism, it is sometimes most useful to know the electric fields, the D or the E field. Meanwhile, in the heat transfer, there is no reason for compute derivatives, our main variable. And in this case, it is necessary. So for example, in this case, one can model a 3D capacitor. In this case, you model the dielectric region between the electrodes, and also you can model the volume surrounding the capacitor, that it can be vacuum, air, or it's, in this case, a 2D model of the same capacitor. So what happens at the interface when fields are computed from an electrostatic model with multiple materials? One can see discontinuities, and these discontinuities arise because we have different materials. So these, in some cases, can have issues when doing multiple materials and computing fields. You can see the way that these fields are computed are with these formulas. You get the gradient of the electric potential, and then you get the E field. And if you want to get the electric flux density, then you multiply it by the relative permittivity and the vacuum permittivity. But as I told you, what if you have the case that you have different relative permittivities and it is inhomogeneous in your model? For example, in this case, in the 2D capacitor, we have a dielectric permittivity different from the vacuum permittivity that is surrounding the capacitor. So in this case, I'm going to compute the solution for a cross-section of a parallel plate capacitor. You can access to this model in the monograph. So we define the variables and the parameters of the equation. If you can see, we are using a piecewise function to define the different values of the relative permittivity, a value of 7 for the dielectric and a value of 1 for the region surrounding the capacitor. Then we define the boundary conditions. They are electric potential conditions. We are applying a voltage difference between the electrodes. Then we compute the electric potential that it returns an interpolating function span over the whole domain. So now that we have this interpolating function, how do we deal with these discontinuities at the interface? The way we did it is by creating a new function that it is discontinuous interpolating function. And in this case, I'm going to show you how you can change this value at this node that it is at the interface of our model. So we call the equation, and what we have in return is a discontinuous interpolating function that will prioritize one of the two values. In this case, the default value, it is 1, 2. 1, 2 refers to the element markers that we use to specify the different material regions. In the left, you can see in orange that it is the dielectric, and in light blue, the vacuum region. So in this case, we are prioritizing this value with this relative permittivity. So this is the way it is done. And after we compute the discontinuous interpolating function, we can compute the electric field. And this is very easy. You can use the grad function. And this is the way it is done. And also, if you want to compute the D field, you can do it using evaluate on element mesh. This function what gives you the capability to evaluate your relative permittivity that we saw, that it is a piecewise function. So this function allows you to compute the D field having different relative permittivities. So here we are also using the default values that will prioritize the dielectric region. After we compute the D field, you can evaluate it at the point that I showed you before, and we have these values. And I wanted to show you that if you change the marker priority, so in this case, now we are going to prioritize the value with the relative permittivity from the air instead that from the dielectric. And you can see already that the values are different. So this new workflow for discontinuities at interface gives you more consistency in your model when you want to compute really specific things, like, for example, forces. You want to know what is the value inside the dielectric, or you want to know the value outside the dielectric at the same interface. So this is the way that it should be done when computing electric fields and you have multiple materials. Then now we can go to our main model that I want to show. It is how to model an electrostatically actuated MEM device. This is taken from this article, inspired from it, and I'm just going to give a quick overview of what is this. Well, a MEM device is a micro-electro mechanical device that typically consists of a thin movable beam or electrodes suspended over a fixed electrode. So in this case, we are going to model these two electrodes. You can see that our top electrode is movable. It is only fixed at the left. And then we have a bottom electrode that it is all fixed. And we apply a voltage difference between these two electrodes. So when applying a voltage difference between two electrodes, we are going to induce surface charge densities over the surface of the electrodes. And these surface charge densities are going to generate an electrostatic force between two electrodes. So as the bottom electrode is fixed, we are going to see only a deformation of the top electrode. It's going to bend in the downwards direction. And this is what we are going to model by coupling the electrostatic simulation with a solid mechanics simulation. In this case, for the surrounding, we are going to use a zero electric potential at the exterior boundaries, and we are going to specify the voltage with an electric potential condition in the electrodes. You can make more complicated this model by adding, for example, different relative permittivities or making it a 3D model, but in this case, we are going just to simulate it in a 2D domain. So first of all, we need to define our mesh. This is really important. The mesh has to be done by removing the electrodes. We always remove the electrodes or the metallic surfaces, or in other words, the conductors from the mesh. So this is the way it is done. Then we define the variables and parameters of our model, and then we generate the electrostatic equation. In this case, it is not necessary to define a relative permittivity. Then we are going to use element markers from the boundary conditions. In this case, it is more easier to define the boundary conditions, where to place them. So in this case, we are going to specify the electric potential conditions in element marker 1. This is the exterior boundaries, and a zero potential also in the element marker 2. That is the bottom electrode. And then we define the electric potential at the top electrode, that is of 20 volts. After solving it, we are going to see this distribution that matches with our boundary conditions. We can see already the voltage difference, and here we can see the gradient of voltages that is going to create this electrostatic force between the electrodes. So the good thing about this model is that you only need to compute once the electrostatic model, and then you can go to the solid mechanics models and do the coupling. So in this case, the solid mechanics coupling is going to be with a pressure. So we already solved the electrostatic model. Then we are going to couple both models with a boundary condition. So in solid mechanics, we have boundary conditions that can specify loads, pressures. So the pressure that we are going to use to express the deformation is going to be a pressure that it is dependent of the electric flux density of our electrostatic model. After computing the pressure with this electric flux density, we compute the deformation using the solid mechanics workflow, and then we update the electric flux density with this new deformation that we achieve. And then we repeat steps from 2 to 4 until we get to a convergence that is going to be the maximal deformation and displacement that we are going to see in our model. So in this case, for the solid mechanic model, we just need to model the top electrode. It's not necessary to simulate the whole domain that we use in the electrostatic model. That brings another advantage, and it's very easy to do it in Mathematica. Then we define our variables and parameters for the solid mechanical analysis. That includes the Young modulus, the Poisson ratio, thickness, and we are going to use a plane stress formulation in this case. Then we define the boundary conditions. We are fixing the left side of the electrode, and then we are specifying the solid boundary load value, where we specify the electrostatic pressure. And the electrostatic pressure function is at the end of our presentation, that this already computes the pressure from the electric flux density. If you see, I'm not going to give a displacement yet for this boundary, and we are going to compute the first deformation. We define the PD component equation, and then we proceed to solve it. So this is going to be our first displacement from the first pressure. And then we are going to do the iteration. In this iteration, we are going to use the displacement in the y directions downwards and the maximal displacement. And this is the value that we are going to use to test if we have get to the convergence. So we are going to compute the relative error of the maximal displacement with the all displacement, and until we reach an accuracy that we want. So in this case, we are going to do the iteration in a while loop with a secondary boundary load value. Here we are going to specify also the electrostatic pressure, and the difference is that now we are giving as an input the displacement that we before computed, and then we solve the model. So if we run this loop, we are going to get to a final displacement of our movable electrode. And at the end, we are going to achieve what we want. So in this case, as you can know, in the solid mechanics, you can do a lot of post-processing, compute stresses, deformations, strains. In this case, we computed the von Mises stress, which is the results that are shown in the article, and they match with what it is given in the article. So we can see here the distribution of the von Mises stress in the deformed top electrode. We can see already the distribution and the deformation that the maximal displacement that we are going to get with these characteristics. So if you can see, the electrostatic model can be coupled already with different physics, for example, the solid mechanics. And well, you can do many things already with just electrostatic equation. Then what about our future work in electromagnetism? As I told you, this is the first of a series of electromagnetics, of how to model electromagnetics. So we are already working on the workflow for electric currents that follows the same principle as in an electrostatic equation. It has the same form, but it applies for conductors. And also magnetic fields and electromagnetic fields. So we want to show you complete workflows for doing complex models, how to couple them, how to compute secondary quantities. And the main idea that I want to let you see is that you can access to these tutorials that will be very helpful for your future projects about how you can use all these new functionalities. And we want to do the same for these fields. And I want to emphasize that you can already simulate these phenomena in electromagnetism, but obviously it requires more work from you to know which equation to use, how to specify boundary conditions, which things we cannot do, and what things we can do. So this is the purpose of doing these monographs, to show you how and what you can simulate with Mathematica and the finite element method that we have. So these are the things that we are working on right now, and this was the first addition that we did with electrostatics. So this is the end of the presentation, and I will be glad to answer you some questions that you have.